What's up, y'all? It's another day to do the Leetcode daily challenge, and today we're going to be solving find all k-distant indices in an array. So we're given an array nums and a key and a k, which are both integers, and basically we're supposed to find all the keys in the array and return a list of all the indices that are within k spaces away from any key value, and return them in increasing order. And also the key values themselves count towards that list. So one idea to approach this problem is to iterate through the nums array, and anytime you find a key value like 9 here, you're going to want a second loop to iterate through all of the spaces that are within k distance. So in this case, one space away. So you would add the 4 to your result. Well, you would actually add the 1 index, and then also the 2, the key itself, and the 3. So all of those would be added to your result, and then you keep going, and you would find also this key value, and then you would do the same thing. But as you can see here, we run into a little bit of an issue where we would be finding this value next to the left of this 9, and that's overlapping. We would be double counting the indices, and we don't want to double count. But it's also not the end of the world if we double count, because we can just remove the duplicates from our result array using a set. If you've ever done the problem contains duplicate, then that should be pretty simple to do. But another main problem with the continuous overlapping here is that worst case, if our k value is very large, and I don't have the constraints here, but I'm pretty sure k can be up to the same length as nums. So if the k value is very large, then we're going to be doing like super long checks on both sides for each number, and then that would be O of n squared. And there's a way we can do better than that with an optimization. So to optimize this, we're really just thinking of a way where we can ensure that we never overlap between two different key checks, but also we want to be able to guarantee that we would still find every indice that matches the criteria without missing any. So the way we can do that is when we iterate on this first key, we would find this index and this index and add all of those to our resulting array. But then once we get to this key, basically we need to keep track of the fact that we already visited up to this 3 index, and there's no need to visit it again. So basically we know that we're going to keep track of this 3 in some sort of variable, and then once we get to the second 9 key, we're going to basically change our left bound so that we only start our search from the 4 index and to the right. And then that would continue on where basically the right bound of this check would be the next minimum value, which is the leftmost index that we have already visited and we don't need to revisit. And I think this will make more sense in the code. So first I'll show the not as great O of n squared method, and then I'll show the optimization, and I think in code it makes a lot more sense. So the first method without the without the optimization is first you're going to make an array with the indexes, and then you're going to iterate through nums, and then if the number you're on is equal to a key, then you're going to be checking everything in its vicinity within k. And so you're going to have another loop where, and this is where it gets kind of interesting, is that where you want to start your loop is I minus k, right? Because that's the range of what could possibly be an index that's k distant to the key. But also you want to make sure that you don't get index out of bounds if I is greater than k, because then if k is greater than I, because then you would be less than 0, right? So you want to take the max of 0 and I minus k as your left bound, and then your right bound, you have to be careful also that, first of all, it's I plus k, and then you have to be careful that you're not going past the possible indices of the array. So you want to take the minimum of I plus k or length of nums. But also you have to remember that the right bound for a for loop is not inclusive, so I plus k plus 1, and then also length of nums, it can stay like that because really the last index is length of nums minus 1. So that's kind of the most complicated part. Then you just have this for loop where you're going to add pretty much every index you see into your indexes array, just like this. And then you're done with that part of the problem. But in this unoptimized part approach, you're going to have to deal with the duplicates. So you can create a new array where basically you're going to be doing like a contains duplicate. If you've done that problem before, you basically just use a set to recognize any of the duplicates and then remove them and add all of the non-duplicates to another array and return that array. So you're going to be checking if the number you're on is not in duplicates, then you're going to add that to the other array and also add that to duplicates so it can't be added again. And then return res. And that's accepted, and let's submit. Pretty decent there, but we can do a lot better. It only beats 22%. So adding the optimization is actually pretty simple. Basically, you want to be updating the right bound of, or actually you want to be updating the left bound of this J for loop by replacing it with the right bound of the previous iteration. And basically we're just going to do that by creating a right variable and set it at 0. And then to make things easier, we're going to make these left and right bounds into variables before. So the left bound is going to be equal to this, and then the right bound is going to be equal to this. And then basically the only small change we're going to make is that we're going to make this max of 0 actually max of R, because we don't want the next iteration to be checking anything before something we've already checked in a previous iteration. So on the first key we find, this R is going to be 0, so it's basically the same as before. But on any subsequent keys that you find, this R will be updated with this, and then that will be the leftmost index that you could visit, and it basically guarantees that you're never going to revisit indices, and you basically don't need these duplicate checks anymore. And I forgot to put this in, but this is just L and R, and you should be good from there. And you can delete all of this and just return your initial array instead of res. And that should work. And submit. And there we go. 4MS, definitely more efficient than the previous approach. And we can do it all in one pass. It's O of n. I forgot to check the time complexity of the previous, but I think, the server is busy, so it's not going to tell us on this either. But I think you can trust me that the previous one was O of n squared, and this was O of n. But other than that, that's all the code, and that's all for today's daily challenge.